And so we need to multiply this by a certain amount. And in the textbook, if you don't have the table with you, or the actual numbers, in figure 33.13 on page 651, they have a table right here, and you can do a crude estimate by going 600, come up here, and you figure out what is the percentage compared to the 555 nanometers. And the textbook had it at about 59%, and which is good enough if you're doing the whole thing by eye, but in reality, it is 0.631, or 63.1%. So you take this maximum amount, 2732 lumens, times the percent degradation, I guess, or the percent that's surviving from the optimum. So 0.631. And it looks like typed wrong, it was 1,723 lumens. 24 rounding off. So the 600 nanometer, our eye, the average human eye, I should say, will perceive it to be 63% as bright as if we're 555 nanometers. So that's on the bulb packages, lumen telling you the amount of brightness, which is ultimately what most people buy bulbs for. Questions?
So at 600, it's going to be 60% as bright as 555.
Yes.
Okay.
So they claim.
And the 683 lumen watts is like,
That's a conversion factor.
so it'll be the same
Yep.
for anything, if it's a 200,000 watt bulb or a
Yep.
0.01 watt bulb.
Yes. If it's a 200,000 watt bulb, you know, at some point, things suddenly change when you get to a limit. At 200,000 watt bulb, I suspect there's gonna be some melting and some changes to the air itself.
Yeah.
But yeah, the spirit of what you're going with, yes,
Okay,
it should be that number.
so F is equal to 683 lumen watts times whatever watts is.
Yep.
Okay.
Where did the 0.631 come from?
Well, you can sort of do it by eye off of this table right here. Or, I looked up and found the table with the actual numbers. I would either give you the 0.631 or I'd give you the table and, you know, just get close enough. So let's just sort of take this and run with it a little bit. I'm now going to be shining light, 510 nanometer light, which is cyan or green, depending upon which source. And I want to know what watt bulb do I need? To have the same brightness. As this. Looks like I started the word what? Oh, it's what watt bulb. There we go. What watt bulb, or what is the, how much power does this thing need to be producing in order to be able to get the same brightness? Now, one amendment, I said the first time it was a 4-watt bulb. That would assume that all the energy that was being used was going right into creating this wavelength of light. There's no loss. All right, so we're just going to reverse the process. I want to get the same brightness, so that's how bright it needs to be. the 1724. And I need to figure out basically how many lumens need to be produced from the bulb. So I take my 1724 divided by, well, based on the table, 510. 510 is right there, move up, I hit this point right here, and it's looking like about 50% based upon just the crude estimate. Is that what you're getting, Nick?
Yeah, pretty close. Somewhere around there.
Would you have come up with a different number?
Nah, probably, would just round it to 50.
Officially, it is, what's that, 510, 50.3. So divided by 0.503. And that'll get me basically this number right here.
I'm getting 3,427.44
Units?
lumens.
So that is what needs to be produced in terms of brightness, knowing that there's gonna be a loss here, and then we convert by, well, we need to divide by 1 watt per 683 lumens. And we end up ultimately with
5.02 watts.
There we go. All right, so this is, no questions here? All right, so this deals with the amount of energy that's basically being sent out related to energy that is, we can actually see. But ultimately, when we're talking about light that we can see, that's great that it sends out light everywhere, but we usually, if we're doing a spotlight especially, we want light to figure out how much light is in one particular direction. So we have two different measures for that. Luminous intensity and illuminance. So luminous intensity symbolized by the letter I. And luminous intensity is basically the luminous flux. So it's how much of the visible light that's being sent out, or the brightness of the light being sent out, divided by what's called the solid angle.
Oh man, that sucks. I'm in EET right now, so I think Omega, and I'm like, oh.
Yeah. Yeah, I'm teaching 152 and 252, which are both the E and M. Yeah, that's in my head too.
Q.
All right, so in terms of units, so the SI units of luminous intensity should be the SI units of luminous flux divided by the SI units of the solid angle, which would be aluminum per steradian.
Ooh.
And let's see if I can find the other ball, which has square on it already. There we go. All right, so when we're talking about solid angle there, so hopefully all of you can imagine this, there's a center to the ball, And I've got this little square right here. And so just imagine that from the center of ball to that square, I've got this, basically this section of light that's within that cone. Here's my attempt at a 3D drawing. So if I've got some section on the outside of the ball like that, the steradian, or the solid angle, is a measure of what this angle is right here. That's captured within that, I keep saying cone. Cones usually are round at the end, but whatever shape this happens to be at the end. Let's do just some analogy on solid angle from the circle. So if I just have a plain old circle with some radius r, if I wrap that radius around here, I get that angle, that's 1 radian. When you're talking about 3 dimensions, if I have 1 steradian, if that's 1 steradian, then this area right here is basically the radius squared. If I go all the way around a circle, my circumference is 2 pi r. And the angle going all the way around, well, I just do the arc length, 2 pi r, divided by the radius, and I get the number of radians that are around the circle. I do something very similar here, that the area of, since I'm going to a new dimension, this is a line divided by the radius. Here we're going to do an area divided by that little patch there. The surface area of a sphere, give you a chance to show off if you know it. What's the surface area of a sphere?
So it's got a 1/3 in it or something on it.
Volume has a 1/3 in it.
It's got a weird fraction in it on it.
Yeah, that's the volume. It's got the weird fraction. The volume is 4/3
There it is.
pi r cubed. That's the volume. But the area, surface area of a sphere, if you take the derivative with respect to r, oh, okay, been too long.
Yeah.
No.
You about to come up with it, John?
I don't know. It's lost me.
You multiply times the exponent, and then you divide, then you subtract 1 from the exponent, so it would be 4 pi r squared. So I take the area and I divide by the size of this patch for 1 steradian, and I get the solid angle. So for an entire sphere, it's 4 pi steradians. Just like it's 2 pi radians for a circle, it's 4 pi steradians for a sphere.
So the omega sine is equal to 4 pi SR.
If we're talking about the entire sphere.
Okay.
If we're talking about just a small section of it, then it's going to be something less than that. So 4 pi is the biggest value this will be. So let's take,
And the steradian is the angle of the 3-dimensional cone.
yes.
And the radius is the circle of the area up front of the cone.
The steradian is the solid angle here.
Right, and the up front is the radius.
That the radius of the sphere is still the radius of the sphere. This is the area that the solid angle hits on the surface, the intersection there, that's r squared, the radius
Right.
squared. Yeah. All right, so. Units. Those lumens per solid angle. That was too much for them to write, so that's also known as a candela. Occasionally you might see it just as candle.
I've seen, pole flashlights, they're measured at candle power.
Ah,
I don't know if that's what that means, but
I would think it would, but it's hard to tell if,
There's like horsepower is not really horse.
like
it's more
before they were
torque.
measured in lumens.
seemed like there was a note I had about, because this is metric, and I'm gonna guess that you weren't dealing with metric.
We're probably just doing it like they did horsepower to relate to,
Yeah,
for people to understand.
illumination, that's the one that gives you foot candles, that's the one I was thinking of.
Yeah, the historical candle power is equal to 1.02 candelas.
Because 1 to 1 would just be too much.
Well, same thing,
Of
horsepower,
course.
horsepower is actually equal to some amount of torque. But they related to horsepower to make people have that connection to horses.
Yeah. Now, what I was pointing out just then, or what struck me just then, was the fact that a candle and a candela are off by 1.02. That they're so close.
1.02, yeah.
1.02, but they're so close, but they couldn't go, let's just make them the same. All right, so that's right, I was about to do an example here. All right, so start with, I got a 7-watt bulb. And it's producing light at 450 nanometers. And let's have it hit, so that would be a bulb, let's just say in the middle of a sphere, just to make it easier. And on this little patch right here, let's make this a 0.2 square meter patch. The radius of my sphere is 3 meters. And I want to know, what is the luminous intensity? So what is I? So we got 2 pieces here. One, we've got to figure out the luminous flux, and then we also have to figure out what the solid angle is. Since we just talked about solid angles, why don't we do that one first? I know that the solid angle is going to be equal to the surface area divided by r squared. My surface area is, for the part that I care about, is 0.2 square meters. And my radius is 3 meters, so that's 3 meters squared. So we end up with 0.2 divided by 9. 0.02 repeating. Units?
There
Meter
is,
squared?
You said there isn't one, and you said
I said a meter squared?
not meter squared.
there is no units?
All right, you can get away with that. There is another unit that we could use. Just like radians you don't have to put down, but you could.
What is it, SR?
Yep, which is,
So is A the area of the sphere, or is A the area of the patch?
A is the area of the patch that we're concerned with. Over here, I was looking at how many steradians are there in the entire sphere. That's why I went with 4 pi in that case.
Okay.
I'm sorry about that. So 0.02 steradians or just 0.02 repeating. Now the reason why you would potentially put SR down, even though you don't have to, is just to make it clear that we're talking about a solid angle. If you do not put it down, then it's mathematically correct, but potentially you could confuse the reader. So, but both are correct. So we now have our denominator here. So 0.0222, however far you feel like writing it. Now we need to figure out what is the luminous flux. And we're gonna go through the exact same process that we just went through.
Is the luminous flux always 683 lumens per watt?
Yes.
Okay.
At least within a reasonable limit.
Yeah.
So we have our watt there, so 7 watts times 683 lumens per watt, which will get us some number.
4,781.
Lumens.
lumens.
And then we have the 4,781 lumens, but we need to multiply times a factor that relates to this specific wavelength here, 450 nanometers. And from the chart,
10%?
yeah, it looks like about 10%.
10%.
And then from the table, see how good we are.
12.3, final guess.
What was your final guess?
12.3.
3.8.
Oh, yeah, I'm way off.
3.8%.
Wow, you're not seeing a whole lot of light at all for that.
Yeah.
Is it a black light?
So black light produces ultraviolet, so we'll be getting close to it.
It's 181.78 lumens.
And so now we can figure out what the luminous intensity is.
Is that 7, 7, 8?
7.8, I thought, is that what you said?
I might have said that, I meant 6, 7, 8.
6, 7, 8?
Yeah,
Yeah.
Is there a 1 there?
no.